Alright guys, now we're in section 9.1, so we're looking at sequences. You can think of a sequence in a couple different ways. A sequence is just a list of numbers, usually associated with some sort of pattern. You can also think of a sequence as a function where the domain is a set of natural numbers. That's why you're going to see the letter N a lot. The natural numbers are the numbers 1, 2, 3, 4, 5, and so on. So for this example, we're being asked to write down the first 5 terms of each sequence. So all we need to do is replace N with the numbers 1 through 5 to find those terms. So for part A, I'm going to find C sub 1, the first term. That will be 1 squared over 2 to the first power. So 1/2 is the first term. So notice I replaced the N here, right? That subscript with the 1, and every N over here also with the 1. So the second term would be 2 squared over 2 squared, which would be 1. The third term is 3 squared over 2 cubed, so that would be 9/8. Keep this going. The fourth term would be 4 squared over 2 to the fourth, which would be 1. And then the fifth term would be 5 squared over 2 to the fifth, which is 25 over 32. So all you're doing is you're inputting the index, right, which number term that you want to find, and replacing N. This next one here, part B, you're going to see this interesting factor right here, -1 to the n minus 1. Anytime you see a -1 to some n or n minus 1 or n plus 1 power, this tells us that what we have is an alternating sequence. And by alternating, I mean it alternates sign between the terms. So the terms will either go positive, negative, or negative, positive, depending on that power of -1. Because this -1 has an exponent of n minus 1, this means the first term will be positive. So we'll see that as we write out our terms. So the first term will be -1 to the 1 minus 1 times 1 over 2 times 1 minus 1. So once again, I'm replacing n with 1 to find the first term. So that will be -1 to the 0 power times 1 over 2 minus 1, which is 1. -1 to the 0 power is +1. So the first term is just 1. Now let's go for the second term. So we have -1 to the 2 minus 1 power times 2 over 2 times 2 minus 1. So we have -1 to the first power, which is -1, times 2 over 3. So this term is -2/3. So see how the first term was positive and the second term was negative. Now let's go ahead and find the third term, D sub 3. So then we replace n with 3, so -1 to the 3 minus 1 power times 3 over 2 times 3 minus 1. So -1 to the 3 minus 1 will be -1 squared. That's going to give us a positive term. Times 3 over 5. So the third term is +3/5. So the terms are going plus, minus, plus. So the next one should be negative. So let's see if we can do this one faster. So -1 to the 4 minus 1 power, so that's 3, times 4 over 2 times 4 minus 1. Now since the -1 is being raised to an odd power, that's going to give us a negative term. So we will have -4 over 7. So you're probably starting to see a pattern with these terms. They're going plus, minus, plus, minus. So we know that the fifth term will be positive. The numerators are all going up by 1. 1, 2, 3, 4. So the numerator should be 5. The denominators are odd numbers, 1, 3, 5, 7. So this one should be 9. So sometimes you can see a pattern and you don't necessarily have to plug in. Of course, there's not a problem if you do that, but this is just a little shortcut if you notice a pattern. Let's look at it from the opposite way. Let's say we're given a sequence and we want to define the a sub n term. So let's take a look at these down here. Part A, 1, 1/2, 3, 1/4, 5, 1/6. I'm going to rewrite this in a different way to help us sort of envision what's happening. I'm seeing 1 and then 2 to the -1, 3, 4 to the negative 1, 5, 6 to the negative 1. Just to kind of see the 1, 2, 3, 4, 5, 6 going on here. I'm also going to add in some exponents. I'm going to say 1 to the first, 3 to the first, 5 to the first. Because what it appears to be happening to me is that the exponent is alternating. The base is n, right? For each of them, the base is just the number of the term. But the exponent is alternating between positive and negative values. And the first one is positive 1. That means the exponent I'm going to put on the negative 1 needs to either be n plus 1 or n minus 1. And I'll just go with n minus 1. I think that one's more common. Although it doesn't matter, n plus 1 would work as well. If you had made the exponent of negative 1n, that would not work because that would make your first term negative. And in this one, the first term, they're all positive. That would have made the exponent in the first term negative, whereas we wanted the exponent here to be a positive 1. So a sub n equals n to the negative 1 to the n minus 1 power. That one's a little bit tricky, I think. Let's take a look at part B. This one's also an alternating sequence. So I know I'm going to have the negative 1. Oops, forgot the 1. Okay, the first term is positive, so I do need the n minus 1 power, or n plus 1, doesn't matter. Either way will give you a first term that is positive. And now I'm seeing the even numbers, 2, 4, 6, 8, 10. So I think that I can just multiply this by 2n. And this one was a little bit easier to figure out. These are all written out explicitly. There is another way to express a sequence, and that is called a recursive sequence. This is a sequence where the first term or the first couple of terms are given to you, and then you have to use them to find the remaining terms. So there's a famous one, you may have heard of it, called the Fibonacci sequence. This is a famous recursive sequence. Here we're given one. It says, write down the first 5 terms given a sub 1 equals negative 1, a sub 2 equals 1, and a sub n equals a to the a sub n minus 2 plus n times a sub n minus 1. So notice that the nth term is defined by the 2 previous terms. So, for example, you can't find the 50th term unless you know the 48th and 49th terms. So this one's a little bit more difficult because you have to know the previous terms. You can't just find any term that you want. So you want to find the first 5. Well, the first 2 are given, so let's write those down. A sub 1 was negative 1. A sub 2 was 1. Now to find a sub 3, I'm going to rewrite the formula, this one here, replacing n with 3. So we need to find a sub 3, we need to find a sub 1 plus n, n is 3 times a sub 2. So I got those subscripts because 3 minus 2 is 1, and 3 minus 1 is 2. So a3 is negative 1 plus 3 times 1, so it's 2. Okay, let's try that again for the 4th term. So a sub 4 would be a sub 2 plus 4 times a sub 3. So that would be 1 plus 4 times 2. So that would be 9. So for all of these, I'm needing the previous 2 terms to find them. So to find the 5th term, we'll need to find the 3rd term plus 5 times the 4th term. So the 3rd term was 2 plus 5 times the 4th term, which was 9. So what is that? 5 times 9, 45, so 47. So another thing we can do with sequences is start adding up the terms. When we do that, we're looking at a sum or a summation. So we have a special notation for that here. It's the Greek letter sigma. It's a shortcut to write out adding up n many terms. And sometimes we'll even be adding up infinitely many terms. And you can tell where to start and stop by here. So you start with the first term, and here it's saying add up to the nth term. So sometimes n will be replaced by a number. Sometimes it will just stay as an n, depending on what you're looking at. Sums have some nice properties, and by the way, these sums will be making a reappearance back. Probably you'll see a little bit in Calculus 1, and then you'll see a lot more of these in Calculus 2. So if you have a constant multiple inside your sum, you can bring it out. If you're adding up 2 sequences, you can add them separately. Same with subtraction. And this one is a little bit weird. What it's telling us is if you don't start with the first one, but you want to use a formula, what you can do is go from 1 to n and then subtract away what you don't want. So we'll be using this formula a little bit later in the notes. So let's just practice writing out sums. Here it's asking us to go from k equals 1 to n and k plus 1 squared. So k is the index, so k varies depending on what it's telling us to add up. So let's try writing this out a little bit. So the first term of the sum would be 1 plus 1 squared plus, and then k is 2, 2 plus 1 squared plus, then k is 3, 3 plus 1 squared. We weren't given a number to stop at, just generally stopping at the nth term, so that would be n plus 1 squared. And now I can simplify this a little bit. I know 1 plus 1, so this would be 2 squared plus 3 squared plus 4 squared plus dot 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 all the way to the n plus 1 term, right, squared. Well, this is actually the nth term, so n plus 1 squared. Sums don't necessarily have to start with k equals 1. For part B, you can see that it starts actually with k equals 3. So just make sure you pay attention to those little details. So it will be negative 1 to the 3 plus 1 power times 2 cubed plus negative 1 to the 4 plus 1 power times 2 to the 4th plus, I'm running out of space here, negative 1 to the 5 plus 1 power times 2 to the 5th plus, and then we'll say dot 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 all the way until negative 1 to the n plus 1 power times 2 to the nth. So once again, we can simplify this. I'm seeing an alternating sequence of terms that we're adding up. The first one would be positive, because negative 1 to the 3 plus 1, negative 1 to the 4th power would be a positive 1, and 2 cubed is 8. So I know it would be 8, and then the next one will be negative. 8 minus 16, and the next one is positive, plus 32, minus, and we keep on going and going until we reached our final term, whatever that would be, right, whatever it's defined to be. Here we're just doing generally the nth term. Now let's try the opposite. Let's try looking at a sum and seeing if we can write it in summation notation using the sigma and the indices. So here I have 2/3 minus 4/9 plus 8/27. Okay, so I'm noticing first of all that it is alternating and that it looks like we're adding up the 11 terms, and this could possibly be defined as n plus 1. I think that works because this first term is positive. So let's go ahead and write it out. It's the sum as k goes from 1 to 11. And then we have negative 1 to the k plus 1 power times 2/3 to the k power. So you have to include this negative 1 factor because of the alternating nature of these terms. For part B on this one, I'm seeing that there's 2 different ways you could look at this. Both of them are perfectly fine, just depending on what you like better, I guess. They're both fine. Each term has this factor of a, and then of course r to an exponent. So one way you could do this is have your k go from 0 to n minus 1. If you choose to go that route, the exponent on r is just k. So the first term is a times r to the 0, which is a. And then the very last term is a times r to the n minus 1. So the top here of your summation doesn't necessarily have to be n. Sometimes you'll see it as n minus 1 or n plus 1 or something else. The second way to do it would be to start with the first term and go to the nth term, but then your exponent would have to be k minus 1. So these 2 ways of expressing it are equivalent. They're both correct, and I don't have a problem with either of them if you gave one or the other. So we have a couple of formulas for sums that you will be needing in Calculus 1. I see this L here. This should be a dot, dot, dot. My iPad and my computer are not getting along again. Okay, so you don't necessarily need to memorize these for this class. You may have a teacher in the future who will want you to know a couple of them. Not me, but there are some. So we're going to practice using these formulas. Notice how they all start from k equals 1 and go to n. That's important because if your sum doesn't have that exactly, you need to account for that. And for example, you can see that in part A. This goes from k equals 0 to 14. Well, the formula for that doesn't match, so we need to just keep that in mind when we use the formula. So the first thing I'm going to do is I'm going to split this apart. Into two separate sums. Okay, I'm just using the properties that we had above. So what I'm noticing is that for this first sum, the 0th term is 0. So because k squared would be 0 squared, that's not really adding anything. So this is not really going to be different from using use this formula right here. So we can go ahead and apply this formula. This is going to be equal to the sum as k goes from 1 to 14 of k squared. Okay, because the 0th term is just 0, so adding 0 won't change it. This one, however, going from 0 to 14 is actually 15 terms, and this is a constant. So normally we write 4n, so it would be 4 times 14, but the 0th term is also 4, so it's going to be 4 times 15. So that is where you have to take into account the fact that it's starting with 0 and going to 14, which is a total of 15 copies of 4. So 15 times 4. Now I'm going to use the formula above for k squared. N is 14, so 14 times 14 plus 1 times 2 times 14 plus 1 over 6 minus 60. Okay, so I have 14 times 15 times, what is that, 29? Over 6 minus 60. Okay, let me just go ahead and type this into my calculator. 14 times 15 times 29 divided by 6 minus 60. So I'm getting 955. Part B, same thing as I mentioned before. Take a look at where the sum begins and ends. It does not begin at k equals 1, it begins at k equals 4. The formula we have for k cubed only starts at k equals 1. So what we can do is actually find the sum as k goes from 1 to 24 of k cubed, and then just subtract away what we don't want. And what we don't want is k goes from 1 to 3. So I'm just applying one of those other properties from above, where you just subtract away what you don't want. So I want to add up the 4th through the 24th terms. So what I'm doing first is adding up the 1st through 24th and then subtracting away the 1st, 2nd, and 3rd, which I don't want. You could also just subtract those term by term if you wanted to, but the formula might be a little bit faster. So now I'm using this formula up here for adding up the cubes. So that's going to be 24 times 24 plus 1 over 2 squared minus 3 times 3 plus 1 over 2 squared. So let's simplify this. So 24 over 2 is 12. 24 plus 1 is 25 minus, here I have 3 times 4 over 2, so 6 squared. Let me go ahead and put these in my calculator. 12 times 25 squared minus 6 squared. Very big number. So I have 89,964.